Right now, if the International Space Station lost pressure, a rescue capsule could reach the crew in hours. That thin margin, that whisper of hope, is what most people picture when they imagine space. But cross an invisible line only 400,000 kilometers away, and every safety net begins to fray. Farther still, the sun itself dims into a distant lamp. Radios begin to lie about the present, and the tools of rescue become unreachable no matter how loud anyone screams. Space does not grow more terrifying because the numbers become larger. It grows more terrifying because each threshold quietly removes another thing that was keeping you alive. And once those thresholds close behind you, they do not reopen. Not for you, not for anyone. If you find this kind of slow, unfolding cosmic dread as fascinating as I do, take a moment to hit that like button and subscribe. It genuinely helps more than you know, and it keeps stories like this one coming. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, get yourself comfortable. Let's begin. "408 kilometers above your head. Right now, 7 people are inside a metal cylinder the length of an American football field. Their orbit takes them around the entire Earth in roughly 92 minutes, which means that over the course of a single day, they see 16 sunrises and 16 sunsets. Every 24 hours, the sun rises and falls on their windows, about the same number of times as it rises and falls on a full calendar month for the rest of us. They live in vacuum. Anything not sealed inside their pressurized modules would either freeze or boil, depending on whether it faced away from the sun or toward it. If the entire outer wall of their home cracked open by even a hand's width, unconsciousness would come in about 15 seconds, and death would arrive not long after. By any sensible definition, the astronauts of the International Space Station live in space. They wear that word proudly. Their patches say it. The cameras show it. And when the young students they speak to on downlinks ask what it feels like to be in space, they smile and say, "This is space." They are telling the truth. But they are also, in a very real sense, still inside Earth. That is the paradox that has to sit at the center of everything that follows. Because in the story of traveling outward, low Earth orbit is not the frontier. It is the last address at which the Postal Service still delivers. It is the last place where the neighbours can hear you shout. It is the last room in the human house, and the astronauts inside it are still enjoying the invisible warmth of the walls, whether they realise it or not. Consider what is actually happening at 400 kilometres up. The atmosphere has not ended. It has thinned to something so faint that the pressure is close to a laboratory vacuum, but individual air molecules still drift up there in numbers large enough to gently drag on the station. That drag is why the crew must occasionally fire thrusters to raise the orbit. The Earth is quite literally pulling their home back down toward it, all day, every day, and engineers must push back. This is the first quiet miracle of low Earth orbit that no diagram in a textbook ever properly conveys. The station is not floating peacefully in a sea of nothing. It is being tugged. It is being held. It has not really left. That gentle tug is one form of connection. There are others, and each of them is a kind of protection that the traveller does not realise they were carrying until the day they leave it behind. The most important protection at that altitude is one that no astronaut can see, touch, or feel, but that keeps them from being cooked in slow, invisible ways. Earth spins on its molten iron core like an enormous warm dynamo, and that motion generates a magnetic field that reaches out into space around the planet in a shape roughly like a teardrop. Scientists call the region enclosed by this field the magnetosphere. On the side facing the sun, the solar wind compresses that teardrop inward until it sits perhaps 10 Earth radii out. On the side facing away, the magnetic field is stretched into a long tail, drawn out sometimes by hundreds of Earth radii, like a windsock in a solar breeze. The magnetosphere is not a solid dome. It is a set of magnetic field lines that catch charged particles and redirect them, mostly toward the poles, where they lose their energy in the upper atmosphere and paint the sky with auroras. Every green shimmer over Alaska, every red curtain over northern Norway, is evidence of Earth's magnetic field doing its silent daily work, catching cosmic ammunition that would otherwise strike unprotected skin. The astronauts on the International Space Station orbit almost entirely inside this magnetic shelter. They sit deep inside the teardrop, well below the region where the magnetic field weakens significantly. The result is that most of the truly dangerous radiation from beyond Earth simply cannot reach them. Galactic cosmic rays, which are the ferocious high-energy particles arriving from ancient supernovae elsewhere in the Milky Way galaxy, are largely deflected. Solar energetic particles, which are the protons flung outward whenever the sun has an angry day, are mostly captured or steered aside. What remains is a background dose that is higher than what you and I experience at sea level, but it is manageable. Astronauts who spend 6 months on the station typically accumulate a radiation dose somewhere in the range of 80 to 160 millisieverts, several times what a nuclear industry worker is permitted to accept in a full year on the ground. That number sounds worrying until you compare it to what waits farther out. On the Artemis One mission, which flew uncrewed but heavily instrumented around the Moon in late 2022, the Orion capsule recorded interplanetary cosmic ray dose rates that were, in fact, somewhat lower than earlier deep space estimates had predicted, but were still meaningfully higher than what a comparable length stay on the station would deliver. And that was for a mission of about 25 days. Stretch a mission to the surface of Mars and back across roughly 900 days, and the numbers begin to press hard against every career limit that space agencies have ever written down. But that is a hazard for later in the story. The astronauts on the station are not there yet. They are still inside the shelter. The magnetic field is still doing its work above them. Space around them looks black and infinite through the cupola windows, but Earth's protection is quietly wrapped around their spacecraft the entire time. Then there is the second connection, and it is one you experience yourself every time you send a message. If an astronaut on the station wants to talk to their spouse in Houston, they open a laptop and dial. The link is not quite a normal phone call. It bounces up through a network of relay satellites called the Tracking and Data Relay Satellite System, and then back down to a ground station on Earth, and finally through terrestrial networks to the family kitchen. But the whole round trip, from lips on orbit to ears on the ground and back, takes less than a second. To the human sitting across the table, the conversation feels ordinary. Delays are so small that they can joke, argue, sing to children, tell bedtime stories in real time. When astronauts play music with children in classrooms below, the students hardly notice any lag at all. That instantaneous conversation is not a luxury. It is one of the deepest safety features of low Earth orbit, and its psychological importance is difficult to overstate. If a bolt jams during a spacewalk, an engineer on the ground can talk the crew through a workaround while the problem is still developing. If someone up there begins to feel unwell, a flight surgeon can ask questions and hear breathing and see the face of the patient at the same instant that the astronaut is asking for help. Every single loose thread that might unravel in orbit is watched by a room full of people who see it happen in the moment it happens. Mission Control in Houston does not simply monitor the station. It is, in a sense, riding along with it. The consoles show the temperature of every cooling loop, the pressure in every module, the position of every valve. Any anomaly that begins to develop is very often noticed on the ground before the crew even knows anything is off. Engineers whose entire careers are devoted to one specific subsystem sit ready to help. If your job is to know everything about the way ammonia flows through the external radiators, then a strange whisper of a pressure reading is your job, and you are staring at it before the astronauts inside have finished breakfast. This is a form of protection so integrated into modern spaceflight that we barely name it, but it exists at every layer. Human eyes are always watching. Human voices can always answer. That connection is not something Earth provides through physics or magnetism. It is something Earth provides through infrastructure, a very expensive, very fragile, very reliable web of ground stations, satellites, protocols, and people who care intensely about the crew above. And now the third form of protection, which is the one that matters most whenever things go badly wrong. At any given moment, there is a spacecraft docked to the International Space Station that is not there to deliver anything. It is there in case the crew needs to leave. When Russian cosmonauts come up on a Soyuz capsule, that capsule stays attached to the station for the duration of their stay. When American, European, or Japanese astronauts come up on a SpaceX Dragon capsule, that Dragon stays attached to the station for the duration of theirs. There is always a lifeboat. There is always more than one. This is not decoration. In 2022, one of the docked Soyuz capsules developed a coolant leak while attached to the station, and the entire program had to quickly assess whether the crew that had ridden up in it would still be able to ride it down in an emergency. Backup plans were assembled. Another Soyuz was eventually flown up empty to replace the damaged one. The point is that the option was real, and it was treated as absolutely non-negotiable. You cannot have humans on the station without a way for them to come home fast. How fast is fast? A Soyuz undocking, deorbit burn, and re-entry can be completed in something like 3.5 hours from the moment the decision is made. A Dragon capsule follows a similar timeline. From the moment an astronaut climbs into the seat and pulls the harness down, they could be sitting on Earth, in the palm of a recovery ship, before the next meal on the ground station schedule. That is astonishing when you sit with it. If the roof leaks and the walls crack and the alarms wail and life support surrenders, the crew of the International Space Station can be home in less time than a working shift. Compare that to any distance beyond the moon, and this becomes almost unbelievable in its generosity. There is nowhere else humans have ever gone in space where they could be back on Earth by the time their coffee is cooled. Low Earth orbit is the only address in the entire outward journey where the ambulance can actually arrive. And when it is not an emergency, when it is only the mundane needs of daily life, the fourth form of protection is quietly working just as hard. Every few weeks, a cargo spacecraft launches from Earth to bring supplies to the station. Sometimes it is a SpaceX Dragon carrying food, science experiments, spare parts, and small treats. Sometimes it is a Northrop Grumman Cygnus. Sometimes it is a Russian Progress. The crew looks forward to these deliveries the way sailors used to look forward to port. Fresh fruit arrives, new shirts, handwritten letters from families, rebuilt exercise equipment. Whatever the station's carefully monitored inventory has begun to run low on shows up on schedule or close to schedule, and if anything critical breaks, the ground can build a replacement, launch it, and dock it within weeks. This is a form of connection so ordinary that we almost forget to call it a protection at all, but it is one. It means that the astronauts on the station do not have to survive with only the tools that were packed at launch. They can be resupplied, they can be re-equipped. If a filter clogs and cannot be cleaned, another one will come. If a laptop dies, another will come. If a medication is needed that was not planned for, it will come. Take these four connections together and step back a moment. Earth is protecting the astronauts from the worst radiation with an invisible magnetic field. Earth is talking to them in real time. Earth is holding a lifeboat under the door for them at all times. Earth is topping up their supplies every few weeks. The station is not a settlement in space. It is a very high room in the tallest apartment building humanity has ever built, and every service that runs to the ground floor is still connected. That is why the psychological environment inside the International Space Station is so remarkable. Astronauts report loneliness, yes, and they report the strangeness of never smelling rain, and they report the ache of missing children. But they very rarely report the specific kind of dread that longer missions will introduce, which is the dread of being genuinely beyond help. Up there, help is always inbound. Always. If you need it in the next hour, help is a Dragon undock away. If you need it in the next month, help is a resupply launch away. If you need it in the next minute, help is a voice in your headset that you know by name. This is the illusion that has to be broken carefully. Because low Earth orbit is, by every technical measure, a hostile environment. There is no air to breathe. The temperature swings by hundreds of degrees between the sunlit and shaded sides of the station every 90 minutes. Small debris left over from decades of satellite launches occasionally forces the crew to shelter inside the docked capsules. Space junk in that altitude regime is a serious and growing problem, and one of the ways the station manages it is by simply moving out of the way when tracking radar predicts a close approach. The vacuum is real, the radiation is real, the danger if the walls fail is instant and severe, and yet, the station has been continuously inhabited since November of 2000. That is more than 2.5 decades of human presence, uninterrupted, in what many people casually call space. No accident has ever killed anyone aboard it. Every serious problem has been solved. That extraordinary safety record is not luck. It is the direct result of every one of those 4 connections working together. Magnetic protection blunts the radiation. Real-time communication catches problems early. Docked lifeboats guarantee escape. Regular resupply keeps the closed system from starving. Remove any one of these 4, and things get harder. Remove all 4, and things get impossible. And every meaningful step outward that follows this moment will remove them, one by one, in a specific order. To understand why, we have to look up. Above the station, higher than any orbit routinely used by humans, there are 2 regions of space that hold this whole story together. They are called the Van Allen belts, and they were discovered by the very first American satellite ever launched, Explorer 1, in 1958. James Van Allen, a physicist at the University of Iowa, had proposed carrying a Geiger counter into orbit to see what levels of radiation the young space age would encounter, and when the data came down, the counter appeared to have gone silent at certain altitudes. It was not silent, it had been overwhelmed. There was so much radiation up there that the instrument had saturated. 2 enormous, donut-shaped regions of charged particles were circling Earth, trapped by the same magnetic field that protects the astronauts below them. The inner belt sits from about 1,000 kilometers up to about 6,000 kilometers up, packed mostly with high-energy protons. The outer belt sits from about 13,000 kilometers up to about 60,000 kilometers up, dominated by high-energy electrons. Between them there is a relatively calm slot. Above and around them, the field weakens and finally lets go. The International Space Station orbits below all of this. It sits underneath the inner belt, sheltered. But any spacecraft leaving Earth for anywhere farther out must, at some point, punch through both belts. There is no way around them without an enormously wasteful trajectory. So every mission that has ever left low Earth orbit for the Moon, or for Mars, or for the outer planets, has spent some period of time transiting a region of naturally trapped radiation that would sicken or kill an unprotected human. The transit is fast. Thankfully, modern trajectory planning gets a crewed capsule through the worst of the belts in a matter of hours. The Apollo spacecraft did it in less than 2, on the way out and again on the way back, and none of the Apollo astronauts suffered detectable acute radiation effects because of it. The Artemis One capsule, on its uncrewed test flight, was fitted with detectors specifically to measure what happens inside the crew cabin. As the vehicle passes through those belts, and the data confirmed what engineers had modelled. The belts are dangerous, but survivable if you are quick and you are shielded and you keep the vehicle oriented so that its densest walls face the highest flux. But the belts do something else, something we do not usually talk about in the language of hazards. They mark a threshold. They are the outer edge of the shelter. They are the fence at the far border of the property. On the near side of that fence, Earth is still doing most of the work of keeping you alive. On the far side of that fence, Earth's magnetic hand has almost let go, and what is out there is a different environment entirely. The International Space Station never crosses that fence. Every human being who has ever lived on the station has stayed inside the shelter, has stayed under the magnetic roof, has stayed in real-time contact, has stayed within reach of a lifeboat that could bring them home in 3.5 hours, and has stayed inside a supply chain that could send anything they urgently needed on the next launch. That is the reason the station feels the way it feels to the astronauts who live there. Beautiful, vast, a little lonely, but not terrifying. Not the specific kind of terrifying that begins to grow the moment you push higher, and higher is where the entire rest of this journey lies. Every mission we're about to follow, every crewed vehicle that any space agency intends to send outward in the next decade, begins with a rocket launch, arrives briefly at an altitude very similar to the station, and then does something that no crewed spacecraft has done in more than 50 years. It fires its engines a second time and leaves. It leaves the atmosphere entirely behind. It leaves the drag of the last thin molecules of Earth's air behind. It leaves the safety of a 3.5-hour ride home behind. And, most importantly, it climbs upward, through the 2 great belts of naturally trapped radiation, and out the far side, into a region where Earth's magnetic field is no longer holding the sky steady. On the first day of April in 2026, 4 astronauts named Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen climbed aboard a spacecraft named Integrity atop a Space Launch System rocket and did exactly that. They rode through the Van Allen belts. They kept climbing. They became the first humans since December of 1972 to travel beyond the shelter of Earth's magnetic field and to look back at the whole planet from farther away than any living person before them. The mission was called Artemis Two. It was a lunar flyby, not a landing. It lasted about 10 days. And it was, in almost every sense that matters, the moment that this entire story truly begins. Because the moment that spacecraft crossed the outer edge of the Van Allen belts, everything the astronauts on the International Space Station take for granted began to change. The magnetic protection thinned. The full spectrum of deep space radiation began to arrive. The communication delay grew from imperceptible into something you could actually notice on a stopwatch. The idea of a 3.5-hour return home became laughable. The nearest port of resupply was, for the first time in a human lifetime, no longer available at all. Everything that will follow in this journey outward starts there. The safest room in the outward journey ends at the outer edge of those belts. Beyond them lies a country that begins peaceful and slowly grows stranger with every 10,000 kilometers of altitude. To understand what actually happens as a crew crosses that threshold, we have to follow those 4 astronauts up and out. And when we do, we begin to see something that no one on the International Space Station has ever had to fully confront. The realization that Earth was doing more for them than they ever knew. The Space Launch System rocket that lifted Integrity off the pad at Kennedy Space Center on the 1st of April in 2026 is the most powerful rocket the American space program has ever flown, with humans on board. It generates more thrust at liftoff than the Saturn V that carried the Apollo astronauts. It burns hotter. Its 4 core stage engines, drawn from the same family that once powered the space shuttle, produced together a thrust that shook every window for kilometers around and left a low, continuous roar that people in nearby coastal towns felt in their chests before their ears could name it. For the first 2 minutes of flight, that vehicle poured energy into the sky at a rate that could power a mid-sized country, and it needed every joule of it, because the mission it was flying was not, in any useful sense, a mission to the same kind of place that the International Space Station lives in. It was a mission out. The distinction matters more than it sounds. Every launch from Earth begins the same way. The rocket clears the tower, tips over onto its intended trajectory, and climbs into an initial orbit somewhere around 200 kilometers up. For most missions in human history, that initial orbit is not just the beginning of the journey. It is the entire journey. Crewed vehicles bound for the station simply refine that orbit until they can meet the outpost in space, dock, and stay. Cargo vehicles do the same. Even satellites that will eventually reach much higher altitudes usually spend some time at that low starting orbit first, checking out their systems. Before firing engines again, Artemis Two spent about 90 minutes there, in the safest part of space, with the magnetosphere still wrapped around the capsule and the ground still able to talk to the crew as if they were down the street. Then the upper stage of the rocket ignited a second time, and everything changed. Engineers call it a translunar injection burn, which is a phrase that sounds technical enough to hide what it actually does. It fires the vehicle out. Not up, out. The change in velocity from the burn is enormous, adding roughly 3 kilometers per second to the spacecraft's speed. And once it is complete, the trajectory of the spacecraft is no longer a circle around Earth. It becomes a long, stretched ellipse that reaches out to the distance of the Moon and beyond. From that instant onward, the capsule is not orbiting Earth in any useful sense. It is falling away from it, coasting slowly upward against gravity, losing speed on the climb, and rising into a region of the sky that the International Space Station has never been anywhere near. Somewhere inside the first few hours of that climb, Integrity and its 4 astronauts crossed the outer boundary of the Van Allen belts. The belts, remember, are the 2 great donut-shaped reservoirs of trapped high-energy particles held in place by Earth's magnetic field. The inner belt is dominated by high-energy protons. The outer belt is dominated by high-energy electrons. Between them there is a relatively quiet slot. Beyond them, the field weakens with distance and, eventually, gives up its grip on the sky altogether. Missions traversing this region are engineered to move through it fast, because dose accumulates with time, and the belts are the last place where any crewed vehicle wants to linger. The Artemis One flight, which flew this same corridor uncrewed in late 2022, carried an entire suite of radiation detectors, specifically designed to measure what happens inside the crew cabin as the vehicle traverses the belts. The data was revelatory in ways that will shape crewed spaceflight for decades. In the worst location inside the capsule, during the transit through the proton belt, dose rates spiked to roughly 287 micrograys per minute. In the best location, sheltered inside the spacecraft's storm shelter geometry, the same event was recorded at only about 134 micrograys per minute. Same vehicle, same moment in time, a factor of 2 difference between one seat and another. And when engineers repositioned the entire spacecraft during one of the transits so that its densest structural walls faced the incoming radiation, dose rates in some detectors dropped by nearly half again. This is the kind of engineering that keeps crews alive. But it is also, importantly, a preview of the philosophy that has to govern every meter of the journey from here on out. In low Earth orbit, radiation was mostly Earth's problem to solve, and Earth solved it with a magnetic field. Beyond the belts, radiation becomes the spacecraft's problem, and the spacecraft has to solve it with mass, orientation, timing, and hope. Beyond the outer edge of the Van Allen belts, Earth's magnetic protection does not vanish all at once. It thins. The field weakens with distance in a smooth, physical way, and by the time a spacecraft is several tens of thousands of kilometers away, the magnetic guardian that was so effective at 400 kilometers has become a whisper, and into that thinning shelter the full radiation environment of interplanetary space begins to arrive. That environment has 2 distinct sources, and it is essential to keep them separate because they are quite different animals. The first is the Sun. For most of its life, the Sun is a relatively steady star, pouring out light and a wind of charged particles that our planet's magnetic field easily deflects. But every so often, especially near the peak of its roughly 11-year activity cycle, the Sun has a bad day. A magnetic knot on its surface snaps. Energy that had been stored in twisted magnetic fields is released all at once, and a burst of charged particles, mostly protons, accelerates outward into the solar system at a significant fraction of the speed of light. If those particles arrive at a crewed vehicle beyond the magnetosphere, and the crew is not sheltered, whole-body doses can rise fast enough to cause acute radiation sickness. In the worst historical solar particle events, the doses would have been enough to kill an unshielded astronaut outright. The Artemis Two mission was deliberately timed at a period near the peak of the current solar cycle. That was not carelessness, it was strategy, because the second source of deep space radiation, the more insidious one, actually decreases when the Sun is loud. The second source is called galactic cosmic radiation. It arrives from beyond the solar system entirely. Most of it comes from ancient supernova explosions elsewhere in the Milky Way galaxy, and its particles have been accelerated across space over millions of years by processes that make even our worst solar flares look modest. Individual galactic cosmic ray particles carry extraordinary energies. Some of them are heavy atomic nuclei, iron and silicon and oxygen and other elements, moving at close to the speed of light, capable of drilling through metal spacecraft walls, through skin, through cells, and through DNA on a single straight line in a single instant. You cannot shield galactic cosmic rays out the way you shield against solar protons. In fact, if you try, you can make the situation worse. When one of those iron nuclei slams into an aluminum spacecraft wall, it does not just stop, it shatters, and it shatters everything nearby, and the pieces continue inward as a spray of secondary particles, including neutrons, which are themselves biologically dangerous. Add too much conventional shielding, and the shower of fragments delivered to the crew inside can exceed what the original single particle would have deposited on its own. This is one of the ugliest engineering problems in all of spaceflight. It is a hazard that resists the intuitive solution. The one thing that reduces galactic cosmic rays is, counterintuitively, an angry sun. When the Sun is active, its magnetic field extends further and pushes harder into the outer solar system, and the tangled turbulence of that expanded influence deflects some of the incoming galactic cosmic rays away from the inner planets. During solar minimum, the reverse happens. The sun quiets, its magnetic influence contracts, and galactic cosmic rays flood inward more freely. This is why Artemis Two flew at solar maximum. The mission planners accepted the higher risk of a solar particle event in exchange for the lower background dose from beyond the galaxy, and they built the spacecraft with a storm shelter so that if the sun did erupt during the flight, the crew could climb into the most heavily shielded region of the vehicle and ride the burst out. That storm shelter, in Orion's case, is not a separate module. It is a repositioning of the crew and a rearrangement of stowage bags, water containers, and equipment around the 4 astronauts, so that the densest available mass sits between them and the incoming radiation. When solar physicists on the ground detect the early signs of a coronal mass ejection heading toward the vehicle, they radio a warning. The crew has, at best, tens of minutes, sometimes only a handful of minutes, depending on the geometry and the energy of the particles arriving. During that window, they climb into the shelter configuration and stay there until the ground releases them. Astronauts who have trained for this describe it as one of the strangest experiences in the whole simulation program. You are packed into a small volume with your crewmates, unable to do much of anything, waiting for a wave of invisible particles to arrive from a source 150 million kilometers away. There is nothing to see. There is no sound. There is no vibration. The dose meter simply climbs, and then, after some hours, it stops climbing, and eventually the ground says the event has passed. You emerge into a vehicle that is unchanged. The sun looks exactly the same as it did the day before. But your accumulated career dose has moved, in a single afternoon, by a measurable amount that will follow you into every future decision about how many more missions you can safely fly and for how long you can safely live inside deep space at all. None of these calculations existed for the crew of the International Space Station. None of these problems even applied to them. Their magnetic ceiling handled the entire complicated business without asking. But for the 4 astronauts aboard Integrity, and for every crew that follows them outward, radiation is now something that must be actively managed. Hour by hour, orientation by orientation, day by day. Every panel wall of the spacecraft is either helping or hurting, depending on the direction of the arriving radiation. Every task the crew performs inside the vehicle is potentially exposed, and every extra day in this environment is another day of cumulative dose that will follow those astronauts through the rest of their biological lives. That is the first thing that leaves you when you cross the belts. The confidence that radiation is somebody else's problem. The second thing that leaves you is the illusion that Earth can help you in real time. Radio signals travel at the speed of light, which is a limit built into the physics of the universe itself. Nothing carrying information can move faster. For a spacecraft in low Earth orbit at 400 kilometers up, the light travel time to the ground is about 1 1/3 milliseconds, imperceptible to any human being. For a spacecraft near the Moon, at a distance of roughly 384,000 kilometers, the same signal takes about 1 1/4 seconds one way and about 2.5 seconds round trip. That is small but noticeable. Long enough that a conversation begins to acquire a slight unnatural rhythm. You speak, you pause, the reply arrives. You pause again. On the Apollo missions, engineers and astronauts train themselves to speak in slightly longer, more self-contained sentences, so that neither party would interrupt the other by accident. It works, and after a while the human brain adapts to the rhythm and forgets to notice it. But this is only the first taste. Because the Moon is close, almost embarrassingly close, in the scale of the outward journey, the next real destination that any crewed program is seriously planning is Mars, and Mars sits at distances that begin, at the very closest, at around 55 million kilometers, and stretch, at the farthest, to more than 400 million kilometers. The light travel time varies with the geometry of the 2 planets' orbits, but at the closest approach the one-way signal takes about 3 minutes. At the farthest, when Mars is on the opposite side of the Sun from Earth, it can approach 22 minutes one way, which means that a round-trip conversation between a crew on Mars and Mission Control could take nearly 44 minutes to complete a single exchange. Try to imagine what that does to the relationship between a spacecraft and the ground. You cannot have a conversation. You can only exchange messages. You send a question, you go do something else. Nearly an hour later, the answer arrives. If it is a good answer, you act on it. If it is not, you ask a clarifying question, and then wait again. If something on the vehicle begins to fail during that hour of waiting, the ground does not know about it yet. If the ground sees a warning sign in telemetry that suggests a failure is beginning, the crew will not know for the length of the outbound signal. Whatever the astronauts choose to do in the meantime, they will be choosing it without the help of the specialists who once could speak into their ears in real time. This is the second protection that peels away as you travel outward. Not radio contact itself. That still works. The deep space network of enormous antennas can hear a whisper from spacecraft billions of kilometers away. Communication in the raw sense endures. What ends is the illusion that Earth is with you. The ground becomes a place that reads your past and answers into your future, and never quite catches up to your present. Astronauts who have flown missions where this delay grew noticeable have described it in a strangely consistent way. They say it feels like Earth becomes a slightly less real place. Everyone at home is still speaking, but they are always speaking about a time that no longer exists. And gradually, as the delay grows and the days of the mission pass, the crew begins to trust each other and their own judgment in a way that they never had to on the station. The Artemis Two mission did not encounter these delays. It was close enough to home that conversations felt nearly normal. But every mission that goes farther will, and the crews are already training for it. Simulations for future Mars missions deliberately impose the full communication delay on the astronauts in training, and the results are illuminating. Crews learn to solve problems entirely inside their own vehicle. They learn to make medical decisions without waiting for a flight surgeon on the ground to advise them. They learn to accept that when Earth eventually replies, it may have missed the moment when the answer would have mattered. Which brings us to the third protection that leaves you as you cross outward. The one that hurts the most in the imagination, and often in reality. On the International Space Station, if an astronaut has a serious medical emergency, they can be inside a Dragon capsule, undocked from the station, decelerating through the atmosphere, and being lifted onto a hospital-equipped recovery vessel in the Pacific Ocean in about 3.5 hours from the moment the decision is made. The station itself has a small medical kit. It has ultrasound equipment. It has enough basic pharmaceuticals to handle common problems and stabilize serious ones. But its greatest medical asset is the ability to send the patient home. That option ends abruptly the moment a spacecraft leaves low Earth orbit for anywhere beyond it. The Artemis Two crew, on their 10-day flight around the moon, could not have been evacuated. If one of them had developed appendicitis on day 4, the other 3 would have had to keep them alive with the medical training they had, using the tools inside the capsule until the mission's own return trajectory brought them back to Earth. That is not a failure of planning. That is physics. Once you have fired the burn that sends you toward the moon, you are on a trajectory that you cannot casually reverse. Getting home requires the moon's gravity to swing you around and set you on a return course. There is no ambulance. There is no faster ride. Any medical crisis has to be handled where it happens. The most famous demonstration of this reality in the entire history of human spaceflight happened in April of 1970. Apollo 13 was on its way to the moon, roughly 320,000 kilometers from Earth, when an oxygen tank in the service module exploded. The command module, which was the only vehicle the crew could actually ride home in, began losing power and oxygen. The engineers on the ground in Houston, working with the 3 astronauts inside the crippled spacecraft, faced a problem that was simple to state and almost impossible to solve. The crew could not turn around. They were on a trajectory that had already committed them to a lunar encounter. Even if they wanted to abort and come home immediately, the only fast way to reverse course would have required firing the main engine on the damaged service module, which everyone agreed was too risky to attempt because no one knew what other systems had been compromised by the explosion. The solution the ground and the crew improvised together has become one of the great stories of engineering under pressure. The crew moved into the lunar module, the small landing craft they had brought along to touch down on the moon, and used it as a lifeboat. Its life support system, sized for 2 astronauts on the lunar surface for about 2 days, had to keep 3 astronauts alive for nearly 4 days. Its engine, meant only for descent and ascent from the moon, had to be fired to nudge the trajectory of the whole stack. The carbon dioxide scrubbers meant for the command module did not fit the sockets in the lunar module, and the engineers on the ground had to invent, on the fly, a way for the crew to attach square filters into round openings using duct tape, plastic bags, and a hose torn from a spacesuit. The crew followed the improvised instructions. It worked. All three of them came home. That story is celebrated, correctly, as a triumph of human ingenuity, but it is worth sitting with what it actually tells us about the geometry of crewed spaceflight beyond the Van Allen belts. The reason Apollo 13 survived was that the accident happened in a very specific corridor, on a very specific mission, with a very specific piece of hardware attached that could be repurposed as a shelter, and with real-time communication delays of only about 1.25 seconds each way. That last detail is the one people forget. It meant that the engineers in Houston could genuinely talk the crew through problems as they emerged. Every question got an answer within seconds. Every proposed fix could be discussed in a live conversation between the ground and the vehicle. The crew was never truly alone with the problem. The three of them, and the entire building full of engineers in Houston, were, in the practical sense, still one team, still solving the same crisis together in the same moment. Not a single one of those conditions will be present on a Mars mission. There will be no lunar module attached to serve as a lifeboat. There will be no real-time consultation with the ground. And whatever failure occurs will have to be solved with what the crew and the vehicle can do together, in delayed correspondence with a home planet whose engineers can only advise on situations that ended hours before their advice arrives. Apollo 13 is not a template for future crewed emergencies beyond low Earth orbit. Apollo 13 is the last time in human history that a serious crewed emergency in deep space was solved with Earth actively in the loop. Every subsequent one will happen alone. Now stretch this out for a Mars mission. 900 days is a reasonable duration for a round-trip crewed voyage to Mars using conventional propulsion. Roughly 240 days out. Roughly 500 days on the surface waiting for planetary alignment, and roughly 240 days back. During that entire time, the crew is inside a closed-system spacecraft or a closed-system surface habitat, and no rescue mission can reach them. If someone becomes gravely ill 6 months into the outbound trip, there is no cavalry. The other astronauts will do what they can with the training and the supplies they have, and they will document what they learn, and everything will continue whether the patient survives or not, because the vehicle cannot turn around. This is the third protection dissolving. Not the presence of Earth, but the reach of Earth. The knowledge that whatever happens, whatever breaks, whatever body fails or system fails, must be solved with what is already inside the walls of the spacecraft. Astronauts who have flown short-duration missions in low Earth orbit describe the transition to the Mars-class mission architecture as a kind of psychological rehearsal for something they cannot fully picture. They know the numbers. They know that if they go, they cannot come back on demand. Everyone who trains for these missions has to sit with that knowledge for years before flying, and everyone who has done so says the same thing. You have to make peace with the vehicle. You have to trust it the way sailors used to trust the wooden hull of a ship in the middle of an ocean crossing. Not because the ship is invincible, but because the ship is all there is. The medical dimension of that autonomy deserves a closer look, because it is the one that most reliably breaks the imagination. Every Mars-class mission architecture that any space agency has seriously studied includes a crew of 4 to 6 people, and among them at least one, and preferably 2, must be qualified to perform some level of surgical and dental intervention, not because those interventions are expected, but because the alternative is unthinkable. If someone on the crew develops appendicitis on day 100 of an 800-day mission, the appendix has to come out inside the vehicle. If someone breaks a tooth, the tooth has to be treated by another crewmate. If someone breaks a bone in a fall during a training exercise on the Martian surface, the bone has to be set on Mars. If someone experiences a severe allergic reaction to a food they did not know they were allergic to, another crewmate has to administer the epinephrine, manage the airway, and, if the reaction escalates, intubate them, using equipment small enough and light enough to have been launched from Earth, with no possibility of transferring the patient to a hospital. Every physician who has thought seriously about these problems arrives at the same uncomfortable conclusion. Some medical emergencies will not be survivable on a Mars-class mission. not because they are inherently fatal on Earth, but because the treatment they require cannot be delivered inside a spacecraft with a crew of 4, a stroke, a heart attack in the wrong window, certain kinds of internal bleeding, certain kinds of infection that spread faster than the available antibiotics can control. Any of these could kill an astronaut who would have survived the same event in a hospital ward on Earth, and everyone involved in the planning knows it. The crews who fly these missions will know it too. They will fly anyway, because they have decided that the mission is worth the risk. But they will fly with the understanding that if a certain kind of unlucky day arrives, no one will be able to save them, and the mission will continue with one fewer person, and the ground will be told about it long after whatever ceremony the crew held aboard the ship has already ended. The fourth protection to fall away is one that we do not usually call a protection at all, but which is what allows the station to remain habitable indefinitely. Resupply. A closed-loop life support system, no matter how good, is not really closed. Some water is lost, some air is lost, filters saturate, sensors drift out of calibration, consumables run down, machinery accumulates wear. On the International Space Station, none of this is a serious problem, because every few weeks a cargo vehicle arrives with everything that has been used up and everything that has broken beyond the crew's ability to fix. If a filter fails and cannot be cleaned, another one is on the next launch. If a rack of equipment stops working, engineers on the ground build a replacement and ship it up. The station's life support is not really a closed system. It is a slowly leaking system with a continuous stream of deliveries topping it up. Any spacecraft flying to Mars will not have that stream. Whatever launches with the crew is, in almost every practical sense, everything they will have for the entire journey. A resupply mission that chased them would take almost as long to arrive as the crew took to leave, and would arrive at a planet where the crew was already surviving or already dead. So the vehicle has to be built with margin, redundancy, and a life support system that is genuinely closed to the highest degree that any human engineering has ever achieved. Water is recovered from urine and from cabin humidity. Oxygen is regenerated from exhaled carbon dioxide when possible. Every consumable is treated as precious. Every failure of the recycling loop is a slow-burning emergency. The Artemis Two mission did not need this level of engineering. 10 days is short enough that the crew simply carried enough consumables to see them through, with margin. The Apollo missions did the same. But every mission architecture aimed at Mars, every design proposal from every space agency serious about sending humans there, has to solve the closed system problem for month after month after month, without the possibility of a top-up. That is a different order of engineering problem, and it is also, quietly, a different kind of psychology. Because the astronauts who fly it will know that their life support system is running down every day, and that no one is coming to refill it. Take these 4 dissolutions together. Radiation stops being Earth's problem and becomes the spacecraft's problem. Communication stops being a conversation and becomes a delayed exchange of messages. Rescue stops being a 3.5-hour ride home and becomes an impossibility for the duration of the flight. Resupply stops being a routine monthly delivery and becomes something that will never happen at all. That is the character of the space between the Van Allen belts and the outer edge of the inner solar system. That is what Artemis Two began to sample on its 10-day flight. That is what any Mars-class mission will live inside for years. And yet, and this is what makes the outward journey so slow to horrify people who study it, none of these changes is dramatic in the way that a movie would show. There is no wall you fly through, no alarm sounds. The astronauts on the Artemis Two mission, looking back at Earth on the second day of their flight, saw a small blue and white sphere hanging in a black window, breathtakingly beautiful, and they saw it because Earth was still, in some sense, right there. The distance to it, roughly 300,000 kilometers by then, is a distance that human minds can just about hold. The Sun, from the same vantage, looked the same size it did from the Kennedy Space Center pad the week before. The stars looked the same. Everything looked, in the moment, extraordinarily familiar. The horror of leaving low Earth orbit is not something the eye can see. It is something the systems have to be told. The crew learns it from the way the flight surgeons no longer answer questions immediately, from the way that a small problem with a valve, which on the station would have been solved by 3 engineers on a phone call in an hour, now has to be worked on by the astronauts themselves for the better part of a day. From the way that the ground, when it does reply, sometimes says, "Please tell us what you have already tried," because we cannot see the current state fast enough to know. The station crew never has to learn any of this. The station crew is still inside the house. The Artemis Two crew were the first people in more than 50 years to step out into the yard. And they did so knowing that the yard is not the frontier either. Beyond the yard, past the moon, past the orbit of Mars, past the belt of asteroids that surrounds the inner solar system, the sky changes character again, in a way that no amount of engineering can fully prepare a spacecraft for. Because out there, the one thing that every solar-powered mission has ever counted on begins, finally and irreversibly, to fail. The sun. The same sun that the astronauts on the station see rise and fall 16 times a day. The same sun that provides every watt of electricity to every panel on every crewed vehicle that has ever flown, begins to grow dim. There is a piece of physics that governs every discussion of the outer solar system, and it is worth stating plainly at the outset, because everything that follows depends on it. The intensity of sunlight falling on a spacecraft does not decrease gently as it travels outward. It decreases as the inverse square of the distance from the sun. Double the distance, and the sunlight reaching a solar panel drops to 1/4 of what it was. Quadruple the distance, and it drops to 1/16. Multiply the distance by 10, and it drops to 1/100th. This is not a curve the human intuition handles well. Our senses are used to lighting that dims linearly as you walk away from a lamp. The universe does not oblige. On the sun's terms, distance is not additive, distance is multiplicative, and multiplicative in the harshest possible way. Consider what this means for a spacecraft leaving Earth. A solar panel that generates 1,000 watts at Earth's orbital distance, which is 1 astronomical unit from the Sun, will generate roughly 430 watts at the orbit of Mars, which sits at about 1.5 astronomical units. That is already a significant loss, and it is one of many reasons why Mars-bound missions have historically had to be conservative about how much power they can spend on any single task. But this is nothing compared to what happens as you push farther. At the orbit of Jupiter, which sits at about 5.2 astronomical units, that same solar panel produces only about 37 watts. It has lost more than 96% of its output. At the orbit of Saturn, at 9.5 astronomical units, the same panel drops below 11 watts. At Uranus, at about 19 astronomical units, it collapses to roughly 2.75 watts. At Neptune, at about 30 astronomical units, it delivers just over 1 watt. The panel is the same size, the sun is the same sun, but it might as well be a distant candle. This is the first, largest, and most unavoidable fact of the outer solar system. You cannot power a serious mission with sunlight past a certain distance, not because the technology is inadequate, but because there is not enough light to catch. The Juno spacecraft, which reached Jupiter in 2016, was the first purely solar-powered mission ever sent to an outer planet. To make it work, engineers had to give it 3 enormous solar panels, each nearly 9 meters long, arranged in a pinwheel around a compact central body. When those panels are fully unfolded, Juno is about the size of a basketball court. And that entire array, spread across a spacecraft the width of an American football field's end zone, generates only about 480 watts at Jupiter, roughly the same power as a few household light bulbs together. That is the state-of-the-art in solar power at the 5th planet, and it required an engineering effort that many at the time considered risky. Every mission that has flown to any outer planet since the Pioneer program has relied on a completely different kind of power source, one that has nothing to do with sunlight at all. That power source is called a radioisotope thermoelectric generator, and every spacecraft that has ever reached the outer solar system has carried one. The Voyagers carry them, Cassini carried them, New Horizons carries one. The concept is simple, even if the engineering is difficult. A small quantity of a radioactive material, usually plutonium-238, is packed inside a heavily shielded container. As the material undergoes natural radioactive decay, it produces heat. Around it, a ring of thermocouples converts some of that heat into electricity. There is no combustion. There are no moving parts. There is nothing to fail catastrophically. The generator simply glows warm and produces a modest but reliable trickle of power for decades. decreasing very slowly as the plutonium's decay reduces the heat output over time. This is how the Voyager spacecraft, launched in 1977, have kept talking to Earth for nearly half a century. Their generators have lost most of their original power. The engineers who manage the missions have been shutting down instruments one by one for years, cutting into muscle and then bone, keeping only the most essential systems alive. Voyager 1's original power output was about 470 watts. Today, it is somewhere around 230 watts, and falling. When the number drops low enough that the remaining instruments cannot function, the mission will end, not because of a failure, but because the fuel simply ran out. Every crewed mission that ever attempts the outer solar system will face the same reality. You cannot rely on the sun. You must bring your own furnace, and your furnace will grow colder over time no matter what you do, and the amount of fuel you can carry sets an upper bound on the years you can survive. But dim sunlight is not the only problem the outer solar system introduces. There is also, and this comes as a genuine shock to many people the first time they read about it, an active radiation environment surrounding Jupiter that dwarfs anything else in the solar system apart from the sun itself. Jupiter has a magnetic field that is the strongest of any planet in the solar system, more than 14 times the strength of Earth's at the cloud tops. That field carves out an enormous magnetosphere around the planet, one so vast that if it glowed visibly in the night sky, it would appear larger than the moon. And, exactly like Earth's magnetosphere, Jupiter's field traps charged particles into radiation belts. Only these are not the belts that Van Allen discovered around Earth. Jupiter's radiation belts are, at their most intense inner regions, thousands of times more energetic. The dose an unshielded human would receive in a matter of hours near Jupiter would be lethal. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, had to be built with radiation-hardened electronics, and even then, its systems slowly degraded over the course of the mission. Late in Galileo's life, individual instruments began behaving strangely because their transistors had been chipped away one particle at a time. The tape recorder started skipping. The onboard computer occasionally reset itself for no reason anyone could diagnose. And these were problems that engineers on Earth could only work around by rewriting software, because the physical hardware, of course, could not be reached. The Juno mission solves this problem partly by keeping most of its orbit far from the worst of the belts, diving in only briefly for each perigove pass, and by building a titanium vault around the electronics with walls a full centimetre thick. Even so, the radiation environment slowly degrades even Juno, and every planned mission to Jupiter's moons has to design carefully around the fact that spending too much time in the wrong region of that magnetosphere will cook the vehicle. Any crewed mission that ever attempts to reach Jupiter, or the moons of Jupiter, will have to solve this problem for humans, not for electronics. And the solutions are not obvious. Titanium walls a centimetre thick are heavy. Wrapping a crew habitat in that kind of shielding requires launching enormous amounts of extra mass to the outer solar system, which requires enormous amounts of extra propellant, which requires enormous amounts of extra everything. The cost curve becomes brutal fast. There are proposals to use water tanks as radiation shielding around the crew, doubling the water as consumable and shield. But every such design faces the same problem. You are trying to build a small nuclear bunker and then transport it across a distance of 500 million kilometers, and Jupiter is only the beginning of the outer solar system. It is barely the doorway. Beyond Jupiter, the environment quiets down again in terms of radiation from local sources. Saturn, Uranus, and Neptune all have magnetospheres, but none of them come close to Jupiter's intensity. What deepens instead is the cold, the darkness, and the time. Consider the distances. A spacecraft coasting to Saturn takes about 7 years. The Cassini mission, one of the most successful planetary explorations ever flown, launched in 1997 and arrived at Saturn in 2004. 7 years in transit, and that was with the help of gravity assists from Venus, Earth, and Jupiter along the way. Voyager 2, which took the classic tour of the outer planets, flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. From launch to Neptune, 12 years. And Voyager was moving fast. Any crewed mission travelling on a comparable trajectory would need to keep humans alive, healthy, and sane inside a closed vehicle for a decade or more. One way, with no possibility of resupply, no possibility of rescue, no possibility of turning around. Every problem discussed so far, every dissolution of protection that began the moment a spacecraft crossed the Van Allen belts, deepens now. And a new set of problems appears alongside them. The most obvious is thermal management. Space is not cold in the way that a winter night is cold. Space is empty. What matters for a spacecraft is not the temperature of the vacuum around it, but the balance between the heat it absorbs from sunlight and the heat it radiates away into darkness. In the inner solar system, spacecraft actually spend most of their engineering effort getting rid of excess heat. Radiators are the main thermal challenge. In the outer solar system, that balance reverses completely. There is almost no sunlight to catch. The vehicle radiates its warmth away into a sky that gives nothing back. Every joule of heat inside the walls has to come from something, and if there is nothing generating it, the walls will drift toward the temperature of the local environment, which past the orbit of Jupiter can be well below -150 degrees Celsius. This is why the radioisotope generators are so essential. They do not just provide electricity, they also provide waste heat, which is used to keep the vehicle's electronics and fuel lines and structural components at temperatures where they can function. On Cassini, on Voyager, on New Horizons, the plutonium is doing thermal work all the time and the electricity is almost a bonus. The moment those generators stop producing heat, the entire vehicle begins to freeze, and any liquid inside it, any propellant, any lubricant, any coolant, will eventually fail to flow. A crewed vehicle at these distances would face a much harder version of the same problem. Humans require a habitat kept at a temperature range that is only a few tens of degrees wide. Below that range, they die. Above it, they die. Maintaining that range with only a trickle of solar power available means burning fuel, in one form or another, continuously for the entire duration of the mission. Everything you carry to keep the crew warm is mass that had to be launched from Earth's surface, and every kilogram you carry required tens of kilograms of propellant to lift. Now consider the communication delay, which was already stretching into the tens of minutes for a Mars mission. At Jupiter's distance, a one-way signal takes between about 35 minutes at closest approach and about 52 minutes at greatest distance. At Saturn, between about 70 and 87 minutes one way. At Uranus, roughly 2.5 hours one way. At Neptune, roughly 4 hours one way. A conversation, if you can call it that, between a crew at Neptune and mission control at Earth would involve 8-hour turnarounds between question and answer. A single yes or no would take a workday to complete. At these distances, Earth is no longer a source of guidance. Earth is a source of history. Whatever the ground says to the crew is already hours out of date by the time it arrives. Whatever the crew says to the ground will be answered in a time frame that no acute emergency could possibly wait for. The astronauts, if they exist, are not really in contact with mission control in any operational sense. They are exchanging letters across a gulf so wide that both ends of the correspondence are essentially writing to strangers. This is not just an inconvenience. It is a psychological environment that no one on the International Space Station has ever had to endure. On the station, if you feel unwell in the middle of the night, you can call down to the flight surgeon and hear a familiar voice on the line before you have finished describing the symptom. At Neptune, if you feel unwell in the middle of the night, you can send a message and then continue feeling unwell for the next 8 hours, alone in a spacecraft with the same 3 or 5 or 7 people you have been alone with for a decade, waiting for a reply from a home that no longer knows what state you are in. And it is here that the fifth protection, one that we have not yet fully addressed, begins to fail in a way that is almost impossible to overstate. That protection is the assumption that equipment can be replaced. Every complex machine that humans build wears out. Bearings degrade, seals fatigue, insulation cracks, software accumulates errors. On Earth, this is not usually a serious problem because we replace components before they fail, or we replace them shortly after they do. On the International Space Station, the same is true. When something breaks that the crew cannot fix, another one is on the next cargo launch. If a critical system develops a fault that cannot wait, an entire redesigned assembly can be built on the ground, tested, and flown up within weeks. The station's continued habitability depends on this constant refreshing of hardware, and no one who works on the program pretends otherwise. A crewed spacecraft flying to Neptune or even to Saturn will not have this option. Every component that launches with the vehicle has to survive for the entire duration of the mission, plus a margin. The seals in the life support system have to hold for a decade. The valves in the propulsion system have to open and close reliably after 10 years of continuous vibration. The pumps in the water recovery loop have to keep pumping without maintenance visits. The electronics have to withstand a decade of accumulated radiation damage, including whatever solar particle events happen to arrive along the way. And when something fails, as things always do, the crew has to fix it with whatever spare parts they packed, or with whatever ingenuity they can improvise, because no cargo vehicle will ever arrive. This is the reality that shaped Voyager engineering half a century ago, and it is why those two spacecraft are still the reference point for how to build a machine that operates for decades in deep space. Every subsystem on Voyager was designed with brutal simplicity, redundant paths, generous margins, and the understanding that any part that broke would stay broken. When one of Voyager One's thruster sets began to degrade after decades of use, engineers on Earth managed to activate a backup set that had been dormant since 1980. Similar tricks have kept the spacecraft functioning far beyond their design lifetimes. But every one of those tricks was possible only because the original engineers, sitting in offices in Pasadena in the 1970s, had thought to include a backup that they never expected would be needed. Every spare that was not built into the original vehicle is a spare that will never exist. A crew in the outer solar system inherits this constraint in the most literal way possible. Whatever failed to be included at launch cannot be added. If a critical medical device breaks, and no one packed a second one, then it is broken forever. If the recycling loop in the life support system develops a flaw that cannot be repaired with onboard tools, then the recycling loop is compromised for the rest of the mission. There is no engineering shop on the ground that can send replacements. There is only the shop inside the vehicle, and it has whatever it has. The life support system inside any outer solar system vehicle would face a slow, cumulative failure mode that no crewed program has ever fully solved, which is that a recycling loop degrades a little bit every time it runs. Every water recovery loop, no matter how well designed, has an efficiency below 100%. Every carbon dioxide scrubber, no matter how carefully engineered, saturates over time and requires either regeneration or replacement. Every oxygen generator, no matter how clever, consumes electrical power and produces trace contaminants that must themselves be removed by other systems. And every one of those subsystems has moving parts or chemical reactions or filter media or membranes that degrade with use. On the International Space Station, this is managed by replacing components on a scheduled basis. A saturated filter is swapped out for a fresh one delivered on the last cargo flight. A worn pump is replaced with a spare. A degraded membrane stack is exchanged for a new one. The station's environmental control systems are, in effect, in a state of constant refurbishment, because the ground never stops sending fresh parts. The recycling loop looks closed from the outside, but from the inside it is really a slowly leaking system with a steady stream of deliveries topping it up. A spacecraft in the outer solar system cannot do any of this. Whatever filter media was launched at the start of the mission is the entire supply. Whatever pumps and membranes and reaction chambers were installed at Earth are the ones that must survive for the entire mission. And when they degrade, which they will, the crew has to work with reduced efficiency, or the crew has to switch to a backup that itself has a finite operating life, or the crew has to accept that a system that used to recover 90% of the water in a given input stream is now recovering only 70%, which means that the vehicle's water reserves are draining faster than they were budgeted to. Imagine what this feels like from inside the vehicle. Every week, the flight engineer runs a check on the recycling efficiency. Every week, the number is slightly worse than the week before. On its own, the change is invisible. But integrated over the full duration of a decade-long mission, that drift adds up to a genuine reduction in the margin between what the crew has and what the crew needs. There is no cargo flight coming to reset the count. There is no ground engineer who can send up a new membrane. There is only the awareness that a system that used to hum along quietly is now humming slightly less well, and that the trend line, extrapolated to the return home, does not look reassuring. This is what a genuinely closed system does over long durations. It teaches the crew, patiently and without drama, that every gram of every consumable is finite. Astronauts who have thought seriously about this describe it as a kind of maritime engineering pushed to an extreme that no ship has ever faced. Sailing ships in the 18th century carried spare sails, spare rope, spare rigging, and a carpenter. And every long voyage was, in part, an exercise in living from that inventory. But sailing ships could also stop at ports along the way, and they usually did. A ship crossing the Pacific in the 1800s might spend 2 or 3 years away from home, but it would land at islands, take on fresh water, buy timber, replace crew, and only occasionally cross a genuinely empty stretch of ocean for weeks at a time. A spacecraft in the outer solar system has no ports. It cannot land anywhere. It cannot restock. The nearest surface it could touch, in the sense of putting boots on the ground, is either a moon of Jupiter or a moon of Saturn, or one of the small icy worlds of the Kuiper Belt. And in every case, that surface offers nothing useful to a human being. No breathable air. No liquid water at temperatures that a human could stand near. No repair shop. No warmth. The surface, if you land on it, becomes another problem, not a solution. And beyond Neptune, past the orbit of the outermost major planet, the situation grows only quieter and colder and slower. The Kuiper Belt begins at roughly 30 astronomical units and extends outward to perhaps 50 astronomical units. It is a broad, thin ring of icy bodies, most of them small, some of them dwarf planets. Pluto orbits within it, Marquet orbits within it. Eris, larger than Pluto, orbits at its outer edge. The New Horizons spacecraft, launched in 2006, flew past Pluto in 2015 after a journey of 9.5 years, and then continued outward, flying past a small Kuiper Belt object called Arrokoth in 2019, and continues outward still. The sunlight at Pluto's distance is roughly 1/1000th of what it is at Earth. If you stood on Pluto's surface at high noon, the sun would appear as a single very bright star. You would still be able to read a book by it, if you were somehow warm enough to hold the book, because human eyes are extraordinarily sensitive and the sun, even at that distance, is still much brighter than a full moon on Earth. But every solar-powered technology becomes essentially useless. Every camera exposure takes minutes. Every operation happens slowly. The vehicle's sense of the day around it is close to the sense of a deep-sea creature that has never seen the surface. Communication delays at Pluto reach about 5.5 hours one way, meaning an 11-hour round trip for a single message and its acknowledgement, and that is only Pluto, at the near edge of the Kuiper Belt. Beyond Pluto, the delay stretches further with every astronomical unit of distance. This is where the meaning of realistic rescue completely evaporates. Not just difficult, not just slow, impossible in principle. If a mission crew at Neptune has a life-threatening medical emergency on a Tuesday afternoon, and Earth learns about it at midnight, and Earth spends the next hour crafting the best possible advice, that advice arrives 4 hours later, which is very early Wednesday morning by the crew's clock. There is no scenario in which help physically arrives. There is only the scenario in which Earth watches and waits and grieves and reads whatever the crew's last messages happen to be. This is not a failure of engineering. This is the geometry of the outer solar system. Distances that light itself takes hours to cross are distances across which no rescue mission can operate. Any physical vehicle would take years to reach the crew, and by the time it did, whatever it was rescuing them from would long since have played out. There is a curious inversion here that is worth pausing on. Down on Earth, the very idea of being unreachable is almost anachronistic. Emergency services can arrive anywhere in a developed country within minutes. Even in remote regions, satellite communication and helicopter access make the difference between life and death for people who fall through wilderness ice or become stranded in mountain storms. The scale of human infrastructure on Earth is such that a person in genuine danger can almost always be reached in some way, and the psychology of modern life is built around that assumption. We do not sit with the possibility of being beyond help. We treat it as a rare, tragic edge case. Every mission that ventures past Jupiter permanently inverts that assumption. The crew is beyond help by default. From the moment the engines fire on the outbound leg, the reachable region ends. Every subsequent day is a day inside a machine that must solve its own problems, contain its own accidents, treat its own wounds, and repair its own systems, or accept the consequences of not being able to. And here is the strangest thing about the environment past Jupiter. It is genuinely quiet. Voyager measurements show that once you are past the intense magnetospheres of the giant planets, the interplanetary environment is not more violent. It is not more dangerous per unit time. Solar wind is thinner. Solar particle events are fainter by the time they reach that far. Even galactic cosmic rays, which continue to strike the vehicle at roughly the same rate as they do throughout the outer heliosphere, are a known and steady background. There are no ambushes. There are no surprises specific to the outer solar system that a well-designed spacecraft cannot handle. What kills you, if anything kills you, is not the environment. It is time. It is the slow accumulation of failures that no one can fix from a distance, the slow degradation of components that no one can replace, the slow narrowing of every margin that was built into the vehicle at launch. It is the fact that every solvable problem must be solved by the crew, and that every unsolvable problem will simply persist until it becomes fatal or until the mission ends by some other route. And around all of this, there is the crew itself. A group of 4 to 6 people, sealed inside a shared volume for years at a time, with no new faces, no new company, no chance to walk out a door and be alone for an afternoon. Every quirk of every crewmate becomes familiar. Every habit becomes an intimacy or an irritation. Every meal is eaten with the same people. Every night is spent in the same small volume. The crew is not just travelling together. It is, functionally, its own civilization, one whose entire population knows every other member by name and by breath and by footstep, and whose social fabric has to hold for a duration longer than most human relationships on Earth manage without a break. Psychologists who work with long-duration crews have documented, in studies stretching back to the Soviet isolation experiments of the 1960s and continuing through the modern Antarctic winter-over programs and the year-long simulated Mars missions run by various space agencies, a consistent pattern. Small crews in prolonged isolation develop, in every case, some form of subgrouping. Alliances form. Someone becomes the person others quietly resent. Someone becomes the peacemaker. Someone becomes withdrawn. Someone becomes overly cheerful, in a way that grates on everyone else. These patterns are not failures of the crew. They are what human beings do when they cannot leave. On the ground, the response is straightforward. Bring in a counselor. Rotate the crew. Give someone a weekend off. In the outer solar system, none of these responses exist. The counselor is many hours away by radio, and by the time the counselor's advice arrives, the moment has passed. The crew cannot rotate. No one can take a weekend off. There is only the same volume, the same faces, the same food, the same sounds of the same machinery, hour after hour, month after month, year after year. Everything the crew brought with them from Earth to entertain themselves, every book, every film, every song, every game, was loaded once and is now finite. Novelty has to be manufactured by the crew themselves. And when it cannot be, the days simply pass, and the walls of the vehicle grow more familiar than the memory of any wall the astronauts ever knew on the planet they came from. The sun, meanwhile, has been dwindling in the sky the whole time. By the orbit of Saturn, it looks perhaps 1/10 the diameter it does from Earth, and delivers about 1% of the illumination. By the orbit of Neptune, it is a bright point of light barely distinguishable from the brightest stars around it. And past Neptune, past the Kuiper Belt, past the frozen slow-motion outer regions of the solar system, the sun continues to shrink. It never quite becomes just another star, but something more strange is about to happen to it, something more consequential than merely growing dim, because the sun's light is only one of its outputs. The other one, the one you cannot see but that has surrounded every human being who has ever lived, the one that fills the entire volume of space we have been travelling through so far, is a wind of charged particles that flows outward from the sun in every direction. That wind creates a vast, invisible bubble around the entire solar system. And past the outer edge of the Kuiper belt, that bubble is finally coming to an end. The traveller who reaches that boundary will cross into a place that no human ever has, and that only 2 spacecraft have ever measured. And on the far side of it, the Sun becomes, for the first time in the outward journey, genuinely alone in a way it never was before. For nearly the whole of this journey outward, one thing has been quietly, invisibly, universally true. The traveller has been inside the Sun's atmosphere. That statement sounds wrong at first hearing. The Sun's atmosphere, we usually assume, ends somewhere just above its glowing surface. The corona, that pearl-coloured halo visible during total eclipses, is often described as the Sun's outer atmosphere, and it extends only a few solar radii out from the surface itself. Everything beyond that, in most people's picture of the solar system, is empty space, vacuum, nothing. That picture is, as it turns out, wrong. Or at least incomplete in a way that changes everything about what it means to travel outward. The Sun does not simply sit in the centre of the solar system, radiating light. It also exhales. Every second, from every point on its surface, the Sun emits a continuous flow of charged particles, mostly protons and electrons, that stream outward in all directions at speeds of roughly 300 to 800 kilometers per second. This flow is called the solar wind, and it fills the entire volume of space we have been travelling through, from just above the Sun's surface to distances so far out that the wind itself begins to slow. The solar wind is not decoration, it is a physical presence. It carries the Sun's magnetic field outward with it, wrapping the field into a vast spiral pattern that spans the whole solar system. It buffets planets, shapes comet tails, drives auroras when it collides with the magnetic fields of Earth or Jupiter, and defines the character of every cubic kilometre of interplanetary space through which any spacecraft has ever flown. Everything about deep space in the vicinity of the Sun is, in some meaningful sense, still inside the Sun. The bubble carved out by that outward blowing wind has a name. It is called the heliosphere, and it has an edge, not a wall, not a sharp discontinuity that you could touch, but a boundary layer, thick and turbulent, where the wind blowing outward from the Sun finally slows enough that the pressure of the surrounding interstellar medium can push back. On one side of that boundary, the environment is dominated by the Sun's wind, the Sun's magnetic field, the Sun's radiation, the Sun's authority. On the other side, the environment is dominated by whatever else is out there, which is the ancient, slow, cold, thin material that fills the space between the stars of the Milky Way galaxy. That boundary is called the heliopause, and exactly 2 spacecraft have ever crossed it. They are Voyager One and Voyager Two, both launched in 1977, both now travelling on trajectories that will carry them outward for the rest of their existence, long after their generators have gone silent, long after every human alive today has died. Voyager One crossed the heliopause in August of 2012 at a distance of about 122 astronomical units from the Sun. Voyager Two crossed it in November of 2018 at a slightly closer distance of about 119 astronomical units. The crossings were confirmed not by any dramatic event, but by careful analysis of the plasma environment surrounding each spacecraft. Because on the far side of the heliopause, the density of the medium jumps abruptly. On the near side, the plasma density is about 0.002 particles per cubic centimetre. On the far side, it rises to about 0.055 particles per cubic centimetre, a factor of roughly 20 times higher. That change, measured directly by instruments on both vehicles, is what told the engineers at the Jet Propulsion Laboratory that the spacecraft had left one environment and entered another. Neither Voyager saw anything. There was nothing to see. There was no light show, no impact, no barrier. There was only a very slow, very quiet change in what the plasma instruments were reporting over the course of hours and days, from one steady state to another. On the far side, the wind of the Sun was gone. The magnetic field patterns had reoriented. The energetic particle counts had rearranged themselves, and the spacecraft, for the first time since it had been assembled on Earth, was drifting through material that had never been touched by the Sun. This is the moment worth pausing on, because it is in many ways the deepest one in this entire outward journey. For every human being who has ever lived, From the earliest hominid on the African savanna to the astronauts aboard the International Space Station today, one thing has been true. They lived inside the sun's bubble. Every atom of the air they breathed had, at some point, been washed by the sun's wind. Every square meter of the ground they walked on was, in some sense, part of the vast circle of matter that the sun holds sway over. Every star they saw in the night sky was seen through the shimmering, invisible medium of the solar wind, streaming past Earth at hundreds of kilometers per second, unseen and unfelt, but everywhere. That is not a mystical statement, it is a physical one. The solar wind fills the entire volume of the solar system. It is thin, unimaginably thin by the standards of anything we would call air, but it is real. Every spacecraft that has ever flown, every planetary probe, every telescope in Earth orbit, every rover on Mars has been immersed in it. The whole of human civilization has existed inside a single vast structure, the heliosphere, that no one on Earth's surface has ever needed to think about, because it is completely transparent to visible light and utterly invisible to the naked eye. The Voyagers stepped out of that structure, and they are the only things human beings have ever built that have done so. From beyond the heliopause, the sun looks different in a way that has nothing to do with brightness. It is, of course, extraordinarily dim by that distance. At Voyager One's current location, the sun is still visible as a bright star, brighter than anything else in the surrounding sky, but no longer the sovereign object that dominates any nearby vantage point. If you were to stand on the Voyager spacecraft and look back toward the inner solar system, you would see a small, brilliant point of light, and around it, nothing that would tell you it was a star with planets. The planets themselves are far too small and dim to see from that distance. Earth, from Voyager One's current position, is a pinprick invisible to human eyes without a telescope. But that is not the strangest thing about looking back from beyond the heliopause. The strangest thing is that the sun, for the first time in the outward journey, is genuinely just one star among many, not the ruler of the local environment, not the source of the wind you are drifting through, not the shaper of the magnetic field you are moving through, just a star. A particular one, admittedly, the one that everyone you have ever known was born beneath, but from beyond the heliopause it exerts no special authority over the immediate surroundings. The wind that fills the local medium comes from other stars, from ancient supernovae, from processes that have been going on for billions of years across the galaxy. The sun's contribution to that mix, at that distance, is negligible. This is what it means to leave the solar system in the deepest possible sense. Not to reach a certain distance. Not to pass a certain planet. Not to cross an orbit or a boundary marked on a chart. It means to leave the region where your own star has any special standing, and to enter the region where your star is a member of a crowd. And here is the fact that ought to sit heavily on anyone contemplating this crossing. That crowd is very sparsely spaced. The nearest star to the Sun is Proxima Centauri, about 4.25 light-years away. In astronomical units, that is roughly 270,000. Voyager 1 has been travelling outward for nearly half a century, and it is only about 165 astronomical units from the Sun. To reach even the nearest star, at Voyager's current speed, would take about 73,000 years. And Proxima Centauri is not on Voyager's route. Voyager is not aimed at any particular star. It is simply drifting through the local neighbourhood, and any close approach it makes to any other star will be a matter of chance and enormous stretches of time. The takeaway is not that interstellar travel is difficult, though it is. The takeaway is that beyond the heliopause, the traveller has entered a region that does not offer any nearby destination at all. There is nowhere to go, there is nothing to reach. There is only the direction the vehicle was pointed at the moment it crossed, and the millennia stretching ahead in that direction, and the slowly changing view of stars that are all, individually, unimaginably far away. Now consider what this means for a hypothetical crew. Any human mission that ever crossed the heliopause would, in that moment, be doing something categorically different from anything humans have done before. Not because the physical environment is more dangerous. It is, in some ways, less dangerous than certain regions of the outer solar system. The local interstellar medium is thin. It has some gas, some dust, some magnetic field, some cosmic rays, but nothing that would kill a well-shielded vehicle more quickly than the outer heliosphere would. In terms of moment-to-moment survival, the far side of the heliopause is not obviously worse than the near side. What it is unreachable in reverse. Every threshold discussed in this journey so far has, in principle, been recoverable. A crew in low Earth orbit could return in 3.5 hours. A crew near the Moon could return in a matter of days. A crew at Mars could, at least in principle, return on the next launch window, though the window itself might be months away. A crew at Jupiter or Saturn could not be rescued during their mission, but their vehicle was still, in principle, on a trajectory that would eventually bring them home, because gravity assist and careful trajectory planning could still make return possible on human timescales. Beyond the heliopause, this is no longer true in any meaningful sense. Voyager One is moving away from the Sun at about 17 kilometers per second, which is faster than any crewed spacecraft has ever moved outbound from Earth. Even at that speed, reversing course would require decelerating from 17 kilometers per second, coming to a stop, and then accelerating back toward the Sun by another 17 kilometers per second, which is a total change in velocity of 34 kilometers per second, which is far beyond the capability of any propulsion system currently attached to Voyager or any crewed vehicle ever designed. The trajectory is, for all practical purposes, permanent. A crew crossing the heliopause would therefore be doing something no one before them has ever done, which is entering a region from which no return is technologically possible with the resources they carry. Not simply difficult, not simply slow, impossible with the ship they arrived in. And there is a psychological weight to that fact that no amount of engineering can prepare a human being for. Every explorer in human history, from the earliest sailors leaving the Mediterranean for the Atlantic, to the astronauts of Apollo 11 walking on the Moon, has known, in some way, that home was reachable, distant, sometimes lethally distant, but reachable. Home was a place you could point at and say, if I turn around now, I can eventually get back there. That belief is one of the deepest things that keeps human beings functional during long voyages. It is what keeps sanity intact during ocean crossings. It is what allowed the Apollo astronauts to look at Earth from the Moon and feel homesick rather than lost. A crew beyond the heliopause loses that belief. Their vehicle is aimed outward. It cannot turn around. The Sun behind them is a bright star, not a home. The nearest star ahead of them is unreachable in their lifetimes. There is no destination. There is only the direction of travel, and the years of consumables aboard the vehicle, and the increasing distance from everything they have ever known. Communication, meanwhile, has stretched to a scale that changes its meaning entirely. From Voyager 1's current position, a radio signal takes about 23 hours to reach Earth one way. A round-trip exchange takes about 46 hours. The engineers at the Jet Propulsion Laboratory who still communicate with Voyager routinely wait nearly 2 full days between sending a command and confirming that the spacecraft has received and executed it. And that is at Voyager 1's current distance, which is only the very beginning of the interstellar region. As distances stretch further outward, communication delays stretch to weeks, to months, to years. At some point, communication ceases to function as communication. It becomes broadcasting into the past. The crew, if there were a crew, would send messages that arrived at Earth years after the events they described. Earth would send messages that arrived years after any question the crew had asked. Both ends of the correspondence would be, in a very real sense, talking to strangers. The person who sent the question would be older or dead by the time the answer came back. The person who received the answer would have moved on with their life, or would never have received it at all, because the vehicle was too far away for its signal to reach Earth with any usable strength. The Voyager missions have a hard end coming for exactly this reason. Their generators are dying. In the next few years, the plutonium-238 in the radioisotope generators will decay to the point where the trickle of remaining power cannot sustain even the most basic instruments. The engineers have been managing this decline for decades, shutting down instruments one by one, retiring subsystems, keeping only the essential. Eventually there will be no essential left. The vehicles will fall silent, still moving outward at 17 kilometers per second, still carrying their golden records, still holding their tiny frozen library of humanity's greetings, but no longer able to say anything back to us. They will drift forever, unpowered, uncommunicating, cold, and their existence will be preserved only by the absence of anything to stop them. That is the future of every vehicle that crosses the heliopause. Whether it carries humans or not, whether it carries instruments or not, whether it was built in California in the 1970s or in some far future factory that has not yet been imagined, the outward crossing is a one-way passage into silence and cold. And this brings us, finally, to the central meaning of the whole journey we have been following. Every step of this story has removed something. Low Earth orbit removes the atmosphere, but keeps the magnetic field, the real-time communication, the 3.5-hour return home, and the monthly resupply. Space feels frightening from the ground, but from inside the station it does not feel deadly, because Earth is still doing so much of the work of keeping the crew alive that the crew rarely has to notice. Beyond the Van Allen belts, the magnetic protection thins. Radiation stops being Earth's problem and becomes the spacecraft's problem. Communication delays grow noticeable, then grow into minutes. Rescue becomes impossible for the duration of the flight. Resupply becomes impossible entirely. The crew learns to solve its own problems, because there is no faster one. Thermal management becomes a constant fight. Equipment must survive for years without maintenance visits. Communication delays grow to hours. Every problem must be solved with what is already inside the walls. Beyond the heliopause, even the sun's atmosphere is left behind. The vehicle enters a region where the sun is just one star among many, where no return is possible with the resources aboard, where communication takes days or years to complete a single exchange, and where the crew, if any exists, has crossed into a country that no human before them has ever entered. At every stage of the journey, the universe itself has not become more violent. The physics of space is the same at Voyager's distance as it is at the International Space Station. The vacuum is the same. Gravity works the same. Light travels at the same speed. Chemistry follows the same rules. There is no monster waiting at the far edge of the solar system. There is no wall of danger past which everything is worse. What changes, and what changes in a specific and progressive way, is not the environment. It is the presence of Earth in it. Near Earth, Earth is everywhere. The magnetic field surrounds you. The voices from home speak into your ear in real time. The lifeboat sits docked outside your door. The next resupply is a few weeks away. Every problem you might have is a problem someone else is helping you solve. You are not really alone. You are, in every meaningful sense, still at home. Space is just the address. At the moon, Earth begins to become a place you can only speak to across a small delay. At Mars, Earth becomes a place that answers your letters within a workday. At Jupiter, Earth becomes a place that reads your history and writes into your future, and you can no longer be sure which state either of you is in when the messages cross. At Neptune, Earth becomes a place you send letters to, knowing they will be received hours later, and the reply will not come for the rest of your working day. At the heliopause, Earth becomes a place that speaks to you across days. Beyond it, Earth becomes a place that speaks to you across years, and eventually not at all. This is the shape of the horror. Not that the universe is empty, it always was. Not that the distances are enormous, they always were. Not that the physics is inhospitable, it always has been. The horror is that as you travel outward, you gradually stop being connected to the only place in the universe that was ever built for you. The astronauts on the International Space Station are not really in space, not in this sense. They are still enclosed by all of Earth's invisible shelters, and every service that reaches them is still connected. The Artemis crews stepping out beyond the Van Allen belts are the first humans in more than 50 years to actually cross that threshold, and they will feel the door close behind them for the whole 10 days of their flight. Any future crew to Mars will spend years in a country where the door is behind them the entire time and cannot be opened. Any future crew to the outer solar system will spend a decade in a country where even the memory of the door is fading. And any future crew across the heliopause, if such a thing ever exists, will spend the rest of their lives in a country where the door was on another continent, another century, another world entirely. The people who study these journeys do not usually put it in these words, because they are engineers and physicists and the language of their profession is measured. But the reality they describe adds up to something that ought to be spoken plainly. Space becomes more horrifying the farther you travel, not because the universe grows crueler, but because the world that made you falls further behind. The atmosphere is left behind, and it does not return. The magnetic field is left behind, and it does not return. Real-time contact is left behind, and it does not return. The lifeboat is left behind, and it does not return. Regular sunlight is left behind, and it does not return. The possibility of resupply is left behind, and it does not return. The reachable window for rescue is left behind, and it does not return. The sun's wind is left behind, and it does not return. Every one of these losses is quiet. None of them arrives with a warning. None of them can be reversed by any known technology. And every one of them is a piece of the world that used to be part of you. The crew that crosses the heliopause has not entered a more dangerous universe. They have simply arrived at the last threshold and looked back and understood that every previous threshold has closed behind them. There is no dramatic ending waiting for them out there. There is no more violent environment past the last one. There is only the slow spreading realization that they are somewhere that no rescue can reach, no message can quickly find, no lifeboat can retrieve, no resupply can restock, no sun can adequately light, and no home can meaningfully hold. The universe around them is, if anything, calmer than the outer heliosphere they just left. But the world they were made for is now unreachable in every way that has ever mattered. That is the final horror. Not that space is empty, not that space is dangerous, but that space, patiently and progressively, and without ever raising its voice, removes every relationship between the traveller and the world that created them. And by the time the traveller understands what has happened, the removals have already occurred and there is no way to undo them. The sun, from beyond the heliopause, is a bright star. It is beautiful. It is still, in some abstract sense, home. But it is a home that is smaller than it has ever appeared to any human eye, and the distance between the traveller and it grows with every second, and no human agency exists that can shorten that distance again. That is what it means to travel outward. That is what waits at the far end of the journey. Not a monster, not a wall, just the quiet, permanent, irreversible separation of the traveller from every hand that was ever capable of reaching them. And the universe, for its part, does not need to do anything else. It only needs to keep the distances the way they are and to let the traveller keep moving. That, in the end, is enough.